Okay, hello again. I'm going to talk about chapter 10 in this video and hopefully finish it. So what I mean by chapter 10, of course, is the rest of this chapter: hyperbola, parabola. I want to talk a little about rotation of axes and also conic sections in polar form. All right, so let us get started here. So I'm going to start with where we left off last time. We were doing ellipses, and here's hyperbola. So last time we talked about ellipses. Now I want to talk about hyperbolas. And hyperbolas are another shape that we get, as we discussed before, when a plane crosses a circular cone. Actually, two of them, right, that share that tip. So if a plane goes through here and hits both of these, the intersections are going to be what? Are going to be hyperbolas, right? All right, now here's some examples of hyperbola in application problems. So when a jet goes over the speed of sound, when the wave hits the ground, the intersection that you get right there is like a plane going through what? These, right? So the intersection that you get is a hyperbola, that shape. Okay? There's also an example of when the crack of a whip occurs because the tip is actually exceeding the speed of sound. That's why you hear that crack. All right. So what does hyperbola look like? Well, hyperbola looks like this. So what we have is, think of an ellipse, right? So let's say you have this. Now suppose we cut this part. Remember, the foci were here, the vertices were here, right? Now let's switch the direction of this way, get rid of that. Now this would be vertex, this would be focus, and the same over here. I'm going to change the direction. Now erase that. This is going to be focus, and this is going to be a vertex, and this is the center. So that's a hyperbola. So hyperbola has actually two foci, ellipse, right? So this is foci number 1, foci number 2, and has two vertices, vertex number 1 and 2, and this is the center. Now an ellipse could be horizontal or vertical, so hyperbola could be horizontal or vertical. So we might have what? A vertical hyperbola, and these are vertices, foci, and the center. Okay, now if we're going to talk more about this, of course, but that's what the shape looks like. Now, just like ellipse, it has two axes, and the axes are this one and this one. This one that contains the vertices is called the transverse axis. The one that has vertices, and also the focus is also in the same line that goes through here, right? So foci and vertices are in this direction, so that's transverse axis. The other axis, the shorter one, now it doesn't have to be shorter, it could be longer, but the other one that doesn't have foci or vertices, that one is called conjugate axis. And these points have also names just like ellipse. They're called covertices. So covertex and covertex. Now there is there are two lines that you can draw, and these two lines are actually the asymptotes of hyperbola. So hyperbola approaches these asymptotes as x goes to infinity or negative infinity. Now if you go from the vertex to the asymptote, you intersected at that point, And that value right here we call B. The distance from the center to the vertex is still called A, just like in ellipse. And the distance from the center to focus is called C, just ellipse. The only difference is that C here is always greater than A, because C is over here and then A is over here. So C is always bigger than A. And A is always the distance we call A that is on transverse axis. So if the hyperbola is vertical, then this distance here is called A, and this distance here is called C, of course, right? And then the distance this way is called B. That makes sense? So A is always the distance measuring on the transverse axis from the center to the vertex. This way we don't get confused, because there is no vertex here to get the distance. That's not a vertex, that's a co-vertex. So if we call that A again, it's confusing. All right, so let's look at how to derive a formula for this. Now, first of all, the definition of a hyperbola geometrically. Remember, the ellipse, the definition was we have 2 points and we're looking for points in the space of the plane, such that when you connect these two, these distances add up to what? A constant, which was 2a in our case, right? So if you find all those points, that you end up drawing what? An ellipse. Now here, the definition is that we have 2 points, right, which are basically foci. The points in space that have this characteristic, I'm going to describe. If you draw from the point to the focus, we get D, let's say D1, and then you go, the distance from the point to focus 2 is D2. Now the characteristic of the hyperbola is that the absolute value of D1 minus D2 is always constant, and it turns out to be 2a here too, but we're going to see. So that constant is 2a based on what? The naming that we give to A. A is the distance from what? From the center to vertex. So if we find all the points that have that characteristic, we end up with these 2 branches of hyperbola. So what we mean here is that the distance from this point to that, if you subtract the green distances and take absolute value, that would be exactly the same if you subtract the red distances and take absolute value. All right. So, and we talked about this already, that what hyperbola has. So I'm going to just go to, you can stop the video and look at this, but I'm going to go to situation where we talked about all that, where we can actually derive the formula. Okay? So here is the way we do it. The easiest way to derive a formula is to put the center at 0, 0. And then we can move it, right? So we put it at 0, 0. Then let's say this point on the hyperbola right here. So obviously we call this A0 because the distance from here to here is A, and the distance from here to here is C. So this point is C0 and this point is A0. Now on the other side, of course, there are negative A0 and negative C0. So here, let's concentrate on this point. So the distance from here to here, the red segment, minus the distance from here to here, which is the green segment, has to be constant. Now we want to know what that constant is based on the naming that we gave to these distances. So what's the distance from here to here, the red distance? Well, this part of it is A, and this part of it is C, right? You go to the left, of course, we call it negative C. But the distance is C units, and this distance is A units, so the whole thing is A plus C, right? And the green distance would be that distance here, which is C, minus that, which is A. So it's C minus A, right? That's the green one. And if you subtract them, these two get canceled, so we get A plus A, which is 2A. So that constant we're looking for is 2A. So we're looking for points in the plane such that if you connect them to the two foci, the absolute value of difference between the two distances is always 2A. Where are those points? Here and here. So now that we know the constant, we pick any point on the hyperbola, which is xy, and do exactly the same thing. We find the distance from xy to that focus, which is going to be what? x2 minus x1 squared plus y2 minus y1 squared. And then the distance from here to here would be x2 minus x1 squared, y2 minus y1 squared, right, square root. And this has to be 2a. Just like we did with ellipse, or we can say just like we didn't do with ellipse, I just showed you what the algebra. We are going to simplify this and get rid of the radicals using algebraic operations like the squaring. But we have to go through it about a page, so I'm going to show you what we get. So we move this to this side first, right? We'll move this to this side, and then square both sides, which is just a little algebra. Then isolate this square root again, right? We get that. Now we square both sides one more time, and we're going to end up with all that. We simplify, and we end up with what? This expression here. Now, we're going to set b squared to be c squared minus a squared, right? Because that's just a number. We just call it what? B squared. And now in the formula here, wherever we see this, we just put b squared. Now we divide everything by what? A squared b squared to make the right hand side 1. So we end up with what? We end up with, let me write it here, x squared over a squared minus y squared over b squared equals to 1. And the connection between A, B, and C is very easy to remember with hyperbola, because it's just like quadratic, it's just like a Pythagorean property. C squared is equal plus B squared. That's what it is. So if we have two of these, we can find the other one. Okay, so this is the equation of a hyperbola. That is what? Notice that one of the variables has a minus and one of them is a plus. We always write the plus one first, and that determines which direction the transverse axis is. So if the transverse axis is horizontal, we write the x first. And then A goes under whatever the transverse axis is. So this one is a horizontal, and the center is at 0. And the vertices are here. How many units to the right and left? This many. So we take a square root of that. That's how many to the left and right. And the focus is going to be somewhere over here, but this is A and this is A. And then vertically from the center you go B units up and B units down. Now A and B could be any size, it doesn't matter. And then we draw this rectangle here. See, once we have A and B, we can draw this rectangle, right? And now once we draw the rectangle, we draw the, what do we call those? Did you say asymptote? Yes. These are the asymptote. And since this is the transverse axis is on horizontal axis, we know this is going to look like this. This is the vertex, right? Draw this back. So it's going to look like that. So if we know A and B and we know it's horizontal, we can easily graph it, right? That's it. And the focus, of course, we can find where the focus is using what? Using this formula. So we can find C and then put the focus here and here, right? Now, if is vertical, then we write the y squared first and we put a squared under it, minus x squared over b squared equals to 1. That tells us that this thing is vertical and the center is at 0, 0. This is a units this way, and this is going to be b units this way, right, in the direction of x. And then we draw this rectangle, kind of like that, and then we draw the, what do we call it? The asymptotes. And you know the vertices now, they're here and here, because vertices are a unit from the center. And the graph will look like this now, right? And the focus is gonna be here somewhere, and we use this formula to find the focus. Okay, so that's the idea. Now, of course, this is center at 0, 0. If the center is not at 0, 0, then it's at HK. We just put them there, right? So this one is a horizontal, right? Transverse axis is horizontal, so it's going to look like this. At this one, transverse axis is vertical, so it's going to look like this when we graph it, right? All right. So let's do some examples. Here we go. So we know this is a horizontal, right? Now the center is at 2, 0. So 2, 0 right there. That's the center. Now, so A is 2 because A squared is 4. So A is 2. That means we have to go 2 units to the right and 2 units to the left. And those are the vertices, vertex number 2, number 1 and 2. And then B squared is 25, so B is 5. So we go 5 units up, right here, and 5 units down. And then we graph our rectangle, the guide rectangle, and graph our asymptotes. And now we know what the graph looks like. The graph looks like, you know, this is the vertex, so it's going to look like this, right? That and that, right? So that's what the graph looks like. Now, where is the focus? Well, we know again, a squared plus b squared equals to c squared. So a squared is 4, b squared is 25. So c squared is 29. So c is square root of 29. Now square root of 29 is about, what, 5 point something? So that means from here, if you add 5 point something to it, it would be like 7 point something. That's one focus. And then from here, 2 minus 5 point something would be like negative 3 point something, would be right here somewhere. So those are the foci. So I let you look at this for a second, and then in the next slide I'm going to calculate I just talked about it, calculate the C, right? Okay, now what are the equations of the asymptotes? Well, the equation of the asymptotes would be, if it's vertical, obviously this is B and this is A, so, and it goes through HK. So what is a line that goes through this point, HK, and has a slope of what? Slope is plus and minus B over A. Because this one has a positive slope and this one has a negative slope. So the line would be y minus k equals to plus and minus B over A times x minus h if it's horizontal. If it's vertical like that, then a rectangle will look like this. But then this line here, this would be A and this would be B, right? Because we call this distance A. So it would be the same because it goes through the center. So it would be y minus k equals to plus and minus A over B and then x minus h. That's the only. In this case, it's horizontal, so it's B over A, and B is 5 and A is 2. So our equations for so this is, in this case, A is 2 and B is 5. So it would be plus and minus 5 over 2, B over A, and then the center is 2, 0, so 2 goes here and 0 goes there. And that would be the equations of the asymptotes, right? All right. And this is another one. So what we have here is find the equation of the hyperbola with asymptotes y equals to plus and minus 2x and vertices at plus and minus 5 and 0. So right away, since vertices are like that, we know, well, it's right here. So we know on the horizontal axis, this is one vertex, and this is another vertex, right? And the center would be right in the middle of them, so that means we know that the center is 0, 0. So right away, we know that we have x squared over something plus y squared minus y squared over something equals to 1. The plus would be an ellipse, right? It has to be minus. And since it's horizontal, x squared goes first, and what goes here should be a squared. Now, what is a? Well, a is the distance from the center to vertex, and we are given that because we know the center, we know the vertex, so that's 5 units. So a is 5. So that would be 25 here. Now, what is b? We are not given b, but we are given the equation of these, right? The equation of that is y equals to 2x. And we know that 2 right there is b over a, right? Now, if we know b over a is 2, and we know that a is 5, so b has to be what? B has to be 10, right? All right, if b is 10, then this is 100, and we are done. We didn't have to graph it, we just had to find the equation, and we did, right? All right, so you can stop the video and look at this again. The calculation is there. All right, so there is another concept, of course, the concept of what? The eccentricity. We talked about that with ellipses. So hyperbolas also have eccentricity. And eccentricity for hyperbola is c over a again. Now, c in hyperbola is always greater than a, right? In a hyperbola, this distance is a, and this distance is c, right? From here to here. That's the focus. So that means in this fraction, c is always greater than a for hyperbola. That means eccentricity for hyperbola is always greater than 1. And the idea of eccentricity is important because when we talk about polar form of sonics, of conic sections, we see that E determines basically what shape we have. So eccentricity for a circle is 0. Why? Because think of a circle as an ellipse. When you make it more circular, the foci approach the center. So if it's really circular, then the center is here and the foci are really close to it. So that means the distance from the center to foci is really small. So C goes to 0 as we make what? An ellipse more circular. And so C becomes really small compared to A, and then E approaches 0. And if it is exactly 0, then we have a circle. Eccentricity of an ellipse, of course, is between 0 and 1 because in ellipse, C always is smaller than A, right? In an ellipse, this distance is C and this distance is A. So for an ellipse, numerator is smaller than denominator. So it's between 0 and 1. And if eccentricity of if is 1 is parabola, then we're going to talk about next. But eccentricity of parabola is 1. And for hyperbola, of course, E is greater than 1. All right, so let's talk about application of, talk about parabolas. Now you have seen parabolas already in algebra. You know y equals to x squared is a parabola. But we want to treat parabolas just like we treated the hyperbola and ellipses. So we're going to think of them as, first of all, the definition of parabola in geometry. A parabola is defined this way. If you have a fixed point, which is the focus, and a fixed line that doesn't go through that point. So the line has to be somewhere else, like could be here, as long as it doesn't go through the point. Now, we're looking for the points in the plane such that if you connect the point to this focus and measure that distance, right, and then draw vertically to the line with a 90-degree angle and calculate this distance, if these are the same, then that point is on a parabola. And this is true for all of these points. You see, these distances are the same, right? So here, of course, this distance equals to this distance, and this is the vertex of the parabola. So the names are the same. We're gonna call this, instead of A's and B's, we're gonna call both of these the letter P, because they're the same. So it's the same distance. So we call it what? Letter P. And here we don't have center really. We only have a vertex and a focus and a directrix. So it's a different naming here. Instead of A, B, C's, we just call this distance P, right? And this is called the directrix. So this is as an equation, either y equals to P, whatever P is, could be negative, positive. And also, now the parabolas could also be horizontal. Now, as I said in this, so far, we only talked about horizontal and vertical conic sections, but very soon I'm going to talk about how we can actually rotate the axes. So, if it's horizontal, then our directrix would be vertical, so it would be x equals to P, right, if it's horizontal. All right, so let's talk about, first of all, some naming here. So this point is the vertex, this point is the focus, and this line is the directrix. That's what it's called. This line right here, not that, that's x-axis. Okay, now the line that goes through here and cuts the graph in half, we know that from algebra, that's axis of symmetry, right? Now, of course, the parabola has diameter But how do we measure this diameter? Well, there are infinite number of diameters here. There is one diameter that goes through the focus. And that diameter is called focal. That length is called the focal diameter. And that has a name. The name of that is lattice rectum. That's what it's called. But the length of it is called focal diameter. Alright, so let's see how we can derive a formula for this. So what we have here is a point on the parabola, and then we have the focus and we have the directrix. So we're going to put the vertex at 0, 0. That makes it easy to derive formulas. And then find the distance from here to here, and find the distance from here to here, and set them equal to each other, right? Now let's do that. So what's the distance from here to here? It would be x2 minus x1 squared, y2 minus y1 squared, and then the blue one is that. You set them equal to each other, square both sides. Simplify. This one cancels that one. This one cancels that one. So this one goes to the other side, becomes a positive 2p pi. 2p pi plus 2p pi is 4p pi. So x squared equals to 4p pi is the equation of the parabola that is vertical. And its focus is here and the directrix here. Now if p is positive, we have a parabola opening up. If p is negative, then we have a parabola that opens down. Focus is here, directrix is here. Now, if we switch the variables, if we have y squared here, and we have 4px, then the parabola is horizontal. Focus is here, directrix here, if p is positive, or is this way and directrix is here. So that gives us more flexibility with parabolas than college algebra, which was just what? Y equals to x squared, or ax squared plus bx, right? Things like that. All right, so let's, So these are general formulas. If the vertices are not at 0, 0, remember we don't have center for parabolas, we just have vertex and focus. So if the vertex is not at 0, 0, then we'll just put it here. The same for the other one, right? So think of algebra, we had like y was to the first power and then was x squared. So if you see x to the second power, that means this is a vertical parabola, either this way or this way, right? But if you see that y is to the second power and x is to the first, you know this is horizontal, right? All right. So again, this is the situation. If p is positive, we have this. If p is negative, we have this. If p positive here, we have opening to the right, and p is negative, opening to the left. This distance from here to here is called the focal diameter, and that distance is of 4p. Okay, so each half of it, of course, is 2p and 2p. But that's what that is. All right. So it turns out, I talked about this already, the focal diameter, that's what it's called, is equal to what? Absolute value of 4p. Let's do an example. Now right away, you know y is to the second and x is to the first, so this is a horizontal. Where is the center? Center is at -1 and 2. So -1 and 2. I mean, not center, vertex. I keep saying center. So vertex is at -1 and 2, right? And now, does it open to the right or to the left? Well, what is P? Let's see. This number has to be what? Now compare it to what? To compare it to 4P and then X minus H, right? So H here is -1 and K is 2, so we got the vertex. So 4P is equal to 12. So what? 3, right? So that means from the vertex I have to go right 3. -1 plus 3 is 2. And I have to left 3. -1 minus 3 is -4. So that's my directrix here, and that's my focus, because I know it opens to the right because P is positive. Now, where do we get the X and Y-intercept? Well, we can substitute 0 for X here and find Y-intercept, substitute for Z here and find the X-intercepts, right? And there is only one X, of course, it goes through X once. So we put Y equal to 0 here. Then that would be 4 equals to 12x plus 12. So 12x equals to -8, right? Equals to -8 over 12, which is, well, -2 over 3, which is right there. So that's the X-intercept right there. And then the Y-intercept, you could just substitute X for 0, 0 for X, and then you get 12, and Y minus 2 equals to plus and minus square root of 12. So Y is 2 plus and minus the square root of 12. The square root of 12 is about 3 point something. So 2 plus 3 point something is 5 point something. So that's 5 point something right there. And then 2 minus 3 point something is -1 point something, which is right there. And now you can graph it. You got the focus, you got all that. Now you can get those 2 points also, because you know if you go 2P up and 2P down, you get 2 more points of parabola, and you can graph it. 2P means 2 times 3, 6. So 6 units up, 6 units down, right? Okay, so I'll let you read this. That's all the work I just talked about. And here is another one. Find the vertex, focus, and directrix. Okay, where is the vertex? Is at -1, 3, right? So -1, 3, -1, 1, 2, 3, right there. So that's my vertex. Is it opening up or down, or vertical or horizontal? Well, notice that y is to the first power. It looks like y equals to x squared, so it's vertical. And what is P? For P has to be -8, so P has to be -2. So absolute value of it is 2. So P equals to -2. That means from here, right, the P equal absolute value of it is 2. So this is the vertex. So I have to go what? And it opens down. So the focus is going to be right here. 2 units below 3, right? 3 minus 2 is 1. And then I have to, the directrix would be above this. So what would that be? 2 units above that. That's the directrix. So we can graph it. So vertex, focus, and the directrix. We got all that. But let me show you the answer right here. So that means this is the directrix, right? The focus is here. This is the vertex. And again, you can get x-intercepts and the y-intercept using this right here, right? All right. Now, the parabola could be represented this way. Now, how is this a parabola? Well, we can complete the square, right? So we can see this part. We put the y's together and see if we can write it as something and move everything else to the other side. So I'm going to move 8x to this side. Now what we have is this, and we complete the square. What do we need to complete the square? Well, we know that if we have, like, let's say y plus b squared, that's y squared plus 2by plus b squared. Now if we have, like, let's say y squared plus 4y, what do I have to add? So I can write it as what? As y plus something squared. Well, what goes here always is half of that squared. What's half of 4? 2. 2 squared is 4. So this would be 2 here. That's called completing the square. You learned that in algebra. So we're going to add 4 here and add 4 to the right hand side. This would be y plus 2 squared, and this would be negative 8x 8. Now, plus 8. This doesn't look like our formula, which is y minus k squared equals to 4px. So what we have to do is we have to make it look like that. X, minus h, right? So we factor the negative 8 out here to write it this way. Now this looks like this formula. So our 4p is negative 8. The y coordinate is negative 2 here of the vertex, and the x coordinate of the vertex is at 1. So the vertex is 1, negative 2. The focus is going to be, well, let's see. So is this vertical or horizontal? It's going to be horizontal, right? So it's horizontal, and where is the 1 and negative 2 is the vertex. Now, does it open down or up? Well, we know 4p is negative 8, so p is negative 2. So it opens what? Opens down, because p is negative, right? P is negative. So opens down this way. So focus is this way. Remember, this is the vertex. So you have to go down 2 units. This is negative 2. Negative 2 minus 2 is negative 4. So the focus is going to be at 1, negative 4. And the directrix would be 2 units above this. The directrix is actually the x-axis itself, right? Because you go 2 units above negative 2, you get that. So we found everything that we were asked to find. Of course, we can graph this, and that's what it looks like. Oh, just a moment. Well, this is, I just said this was horizontal, but I did it vertically. So you have to go this way, right? My fault. I just said it was this horizontal. So this is the vertex. So in order to find the focus, this opens to the left because p is negative, so it's this way. So focus is this way. So we go 2 units to the left. We go to, we get to this point right here. Erase that too. 2 units to the left is the focus. 2 units to the right. 2 units to the right is the directrix. So that's what it is. So that's the focus right there, and that's the directrix. Sorry about that. All right. So, but I'm not going to edit the video because it takes a long time to edit, and it's a natural thing to make mistakes. Okay, so read this, go over it one more time. And I'm going to do an application of parabolas. Now, one thing about parabolas is that if you have a parabola surface that looks like a parabola, well, we can make it a 3D parabola. Parabola is like a paraboloid. So if you take this and rotate it, you make a surface that is called paraboloid. and we can make the surface of it reflective and put a light at the focus, right? Now, the light rays hit the surface here, right? What happens, it has a characteristic, the parabola, that all of these rays will go straight out horizontally. So what happens, this one that goes straight, this goes straight back up. Everything here, it reflects back horizontally. So create a beam of light using a paraboloid, right? You can also reverse this process and build an antenna. So put the receiver at focus here, and then assume that all the rays, all the waves come from distance, they're all parallel like that, and they're going to hit the surface here. What happens when you hit the surface? Well, the wave hit the surface. They're going to reflect back to the focus. So this way we can actually accumulate voltage right here at the receiver. So all of these waves are going to create voltage in the receiver. The electromagnetic, is their fields, right? So they create voltage here. You can accumulate voltage at the receiver. So that's how we can use this paraboloid. Now here we have a satellite dish. Is to be constructed in the shape of a paraboloid of revolution if the receiver placed at the focus is located 2 feet above the vertex of the dish, and the dish is to be 12 feet wide. How deep will the dish be? So the easiest way to do it is to put the vertex at 0, 0 and let it go open up, right? So, and now we know the focus is 2 feet above here. That's the focus. And we know this has to be how wide? It has to be 12 feet wide. So this distance has to be 12 feet from here all the way to here, right? So we can write equations for this easily. So let's do that and solve this. So I have it here, you see. So what is the equation for when we have a vertical one? This is x squared equals to what? X squared equals to 4py. Here we know what p is because we know the distance here. So we put a 2 there. So that would be what? That would be 8. So 8y. This is the equation of this parabola, right? Now, if this distance is 12 units, that means what? That means we have to go 6 units to the right and 6 units to the left. So from 0, 0, if you go to the right 6 units, you get to 6 and then -6. So to find how deep the dish has to be, we just put 6 for what? For x. So 36 equals to 8y, so y equals to 36 over 8, and take, 36 over 8 is 4.5. So how deep should the dish be? 0.5 feet, right? And that's it. All right. Now, here's something interesting. All the conic sections can be represented by an equation like this. Now, it has x squared, y squared, and xy term, and xy, and a constant. It turns out that all the ones that we so far we have talked about don't have that one. The addition of xy to this equation, what it does to our conic sections is that it makes them diagonal. So far we talked about like horizontal ellipses and vertical ellipses. If you have this term, then we have an ellipse that kind of looks like that. It has what is diagonal. So how do we deal with those? Well, we're not going to be able to convert it to these nice forms that we learned. You know why? Because that is xy term. We can't complete the square here. We can't complete the square for x and y. because we don't have xy in completing the square, right? You complete the square, like x plus b squared, we have x squared, or we can make this y, doesn't matter, plus 2bx plus b squared. So there is no x, we can find this form. So what do we do to make these actually like the ones that we've been working on? Well, we are going to eliminate this by rotating the axes. How? We're going to talk about. So first of all, let me show you what I mean when I say these things actually are conic sections. So let's go to this side and actually graph some of these, and you see that I didn't lie to you. So you see, so this is the equation. First of all, what I'm going to do, I'm going to mess with this b, which is coefficient of x, y, right? And I'm going to make it 0. Right about there. You see? Now, when I mess with the other coefficients, I can make different what? I can make different conic sections when I change those coefficients. You see that? I can make different conic sections just by changing those numbers. You see, as you see right there. Now, if this number and this number are the same, we got the circle, right? See that? This is a circle. And of course, we get, we can get a ellipse. We can get, this is an ellipse. We can get hyperbola, parabola, and all that. Now, as soon as I change this b, look what happens. It rotates it, you see? So that xy term just rotates our conic section, right? All right, so I hope that gave you a better visual of what I mean by this. So now, how do we deal with them? It turns out that if we rotate the axes, right, then the stuff that we can write in terms of x and y nicely with our standard formulas, we can actually do if we change the reference axes. How do we do that? We rotate them. So when you rotate the x and a y axis, you get new coordinate system with x prime and y prime axes. So if we have a point, let's say over here, and the coordinates of this point, let's say are, let's say 1 and 2, 1 and 4, let's just call them x and y, right? We don't know what they are. Now, under the other system, the same point, right? The same point under x prime, y prime has two different coordinates, you see? Those will be the coordinates. That would be y prime, that would be x prime. So the same point is represented by two different coordinate systems. The red one and the green one, right? So that's the trick, that first we are going to learn how to rotate, and then we're going to learn how to find that angle of rotation, okay? Now, first of all, how to rotate, we talked about this in trigonometry, and that's how we rotate a point. If you have a point, you want to rotate it theta degrees, just multiply it by this matrix. And the reason is that when this point, when you want to rotate a certain, let's say I want to rotate x-axis theta degrees. So if I have a point here and rotate it, I want it to go there, then I can multiply it by this matrix and it rotates. And the reason is this. The reason is that if I have a point here and I want to rotate it, let's say theta degrees, that much, then we're going to get this. And the coordinates of, so let me use x and y axis. So I want x to rotate this much, and I want y to rotate that much, right? Right here. So the connection between the coordinates of this point and this point with the original to the original points give us this matrix. So if I change x and y coordinates of the old point using these, I could get the rotation. So the way we do this is by multiplication. This is cosine theta times that, negative sine theta times this, and we add them. And multiply this row by this column, we get this. So here, if I want to get rid of, if I want to get rid of this, if I rotate certain number of degrees, what this is, we're going to talk about. If I rotate that many degrees, then this term would go away in here. So we're not going to have this term in here. If I rotate the right amount. And that's what we're going to talk about, how much. First of all, how do we rotate? And then how much should we rotate? Now to rotate the axis and write the equation of a conic section using x prime, y prime, you have to use this conversion. So you have to substitute all of that for x, wherever you see x, and you have all of that for wherever you see y, right? So wherever you see y, you substitute that. That's the idea. So let's do it. And first of all, let's look at again what I mean by rotation. So what do I mean by rotation? I mean this. See, if you have all of these points and you want to rotate them certain number of degrees, you can multiply every point by that matrix that I talked about, right? Now we can do that at the same time. If you put all the points as column of one matrix, you can do that at the same time. So when you multiply by this matrix, you're actually rotating every point this many degrees, alpha degrees. So what I'm going to do, I'm going to go from 0, and then as I change that alpha, computer quickly calculates the new coordinates and graphs them, you see. That's the rotation. So you can rotate every shape like that. Not only these points are going to get rotated, but you can apply it to all the points that create the shape, so the whole shape rotates. So let us do an example of rotation. So suppose I want to represent this in an x prime, y prime system by turning it, rotating the axis by 45 degrees. So this becomes cosine 45, sine 45, sine 45, cosine 45, which is basically square root of 2, square root of 2, right? Over 2. So we're going to take the x's that we have in this equation and convert them using this formula. This times this gives us this right here, and this row times this gives us this one. Simplify. So this is my x in terms of x prime, y prime, and this is my y in terms of what? X prime, y prime. So I'm going to take these, substitute for x here and for x here, and I'm going to take this, substitute for y here and for y there, and then do the algebra. I'm not going to show all the algebra here. It's about a page of algebra. But if you simplify it, you end up with that. And if you move the 60 to the other side, you can divide everything by 60 to get in this form, which is our familiar form for an ellipse. Now notice here, there was no way, with the existence of this xy, there was no way you could convert that to this form. But by this trick, which is rotation of 45 degrees, that is gone, right? Now if you rotate this by 30 degrees, you get a new equation that would not look like this, will look like this, but with different numbers and different x prime and y prime, right? But would not look like what? Would not look like the one that we have here, which is the nice looking one, the standard form. So think about it. It's like you turn your neck 45 degrees, and now it looks like we are dealing with a horizontal what? With a horizontal ellipse. So we can use the same formulas, but don't turn your head back until you finish calculating everything. You can calculate focus and everything. Then when you're done, you turn your neck back straight, right? So that's the idea. All right, now the question is, how do we know how much do we have to rotate in order to get rid of this? And the answer is, and you can read this in the text as well, but the answer is this. If you rotate with an angle such that this equation is satisfied, then that would get rid of the xy term. Now, how do we set this up? Well, that's easy. Look at this equation and notice that these coefficients are in order, right? So b has to be the coefficient of xy, a is the coefficient of x squared, and c is the coefficient of y squared. So if you make sure cotangent of 2 theta is a minus c over b, then that theta would work. So if cotangent of 2 theta is positive, well, remember in trigonometry, if cotangent of an angle is positive, then the angle is in the first quadrant, right? If it's positive in one complete period, which is pi. So it's in the first quadrant, so the 2 theta would be in the first quadrant between 0 and 90. Then theta has to be between 0 and 45, because we have to do, right? So if cotangent of 2 theta, that means if this number is positive number, then theta is between 0 and 45. If the cotangent of number is negative, that means the angle has to be in the second quadrant. That means 2 theta has to be between 90 and 2 theta has to be between 90 and 180. And if you divide by 2, you get theta is between 45 and 90. And that's what you get. And if a and c are equal, you get 0. And if cotangent is 0, if cotangent of 2 theta is 0, then the angle has to be what? 90 degrees, because cotangent of 90 is 0. So if 2 theta is 90, then theta has to be 45. And that's exactly why we rotated the previous problem by 45 degrees. Why? Because A and C were the same, so we knew, or the people who made the problem knew, that 45 degrees would get rid of that in xy prime coordinate plane, right? And that's what actually happened. Okay, so let's find a theta. Suppose we are given this and we are told to find theta that works. Now, to do this, we don't really need theta. What we need is the sine of theta and cosine of theta, right? That's what goes in our formula. So to find that, we start with what cotangent to theta is supposed to be. A here is 8, C is -17, and B is -12. So we set it up, we get 3 over 4. So we know that our theta, our 2 theta, is an angle in the first quadrant such that its cotangent is 3 over 4. Now cotangent is adjacent over opposite. So if cotangent of something is 3 over 4, that means this is 3, this is 4. And by Pythagorean property, we can find that to be 5, right? So now we can easily see that sine of 2 theta is this over that. But we don't want sine of 2 theta, this over that. But we don't want sine of 2 theta, we want sine of theta. From trigonometric identities, we know there is a connection between sine and cosine, right? And cosine and cosine of 2 theta, half angle formulas, right? So what is sine theta? Well, sine theta is the square root of 1 minus cosine 2 theta over 2. What's cosine 2 theta? 3 over 5. So we put it there. We calculate the sine of theta. What's cosine theta? 1 plus cosine 2 theta over 2. Cosine 2 theta, again, 3 over 5. We calculate. So this is sine, and this is cosine theta. Remember, in our matrix, we had what? We had cosine theta, negative sine theta, right? And we had sine theta, we had cosine theta. So basically we have our matrix, right? That's what it is. We use the matrix to find our x and y, and I didn't do all that. I just showed you what we get. In general, we have formulas, we can use them. Instead of using the matrix, we can use these two formulas. So we substitute what cosine and sine are. And now, this is the simplified form of these, right? So we're going to take that and substitute it in here and also in here for x, right? And then we're going to take this and substitute it in here for y, right? Right? That one. All right, simplify. If we do that, we end up with this, and if you divide everything by 100, you get what? You get x prime over 2 over 4 plus y prime to the second, over 1 equals to 1, right? If you divide everything by 100, that's what you get. So as you see, this is what? This is a nice what? Nice ellipse that is horizontal, but not in the way that, not in the regular xy coordinate plane. If you turn xy coordinate plane as much as theta. Now what is theta? Well, we can find with sine inverse and find what theta is that has this. And in fact, we can do that quickly. See what is the theta, because we don't know what that is. Where's my calculator? So I'm going to move it to degree. It's already in degree. So I'm just going to do sine inverse of, what was the sine? Is 1 over square root of 5. 1 over square root of 5. So it's about point, am I in degree in mode? Yeah, I'm in degree mode. So it's a very, very small degree. No, I didn't do sine inverse. Sine inverse, the second didn't work. 1 divided by square root of 5. Oh, my second keeps not working. All right, there you go. So it's 26.5 degrees. So if you rotate the axis about 26 degrees, right? Then we could just consider these axes and graph this, right? So that means this is in the x prime direction, right? So it's going to be in the x prime direction, kind of. You work with x, look like that, right? So it's easy to work with even the ones that are slanted. All right, now all of that we did becomes really difficult when we get to equations of, for example, the movement of the planet Earth around the sun. Those equations require more, much more complicated expressions. So it turns out that polar form makes things much simpler to work with. So instead of working with xy, we can work with theta and r, right? Remember in polar? Now we can write equations of all conic sections using r and theta in polar. And Kepler did that. Kepler, with the equations of the movement of planets on their orbits, using polar made it much easier to work with. So how do we do that? Well, in polar form, all we need is the polar axis. We always put one focus at pole, and then we work with one directrix. So we can define all the conic sections based on three things, three characteristics: a single focus, a fixed line called the directrix, and the ratio of the distances of each to a point on the graph. So for example, if we define a parabola like this, for example, then what we have is what? All the points will have the ratio of what? This distance over this distance would be 1. If that's the case, then we have a parabola in polar form, and the rest of them. So hyperbola, we're going to define it so that the ratio of the ratio that we have here, the ratio of the distances, is greater than 1. And if it's between 0 and 1, we have an ellipse. That's the idea. So the pole has the focus, right? And the directrix is right here. Now, it could be horizontal sections, or it could also be vertical conic sections. We could also have things like this, right? We can have a parabola this way, or we can have a parabola where it opens this way, right? Well, like this way, right? The focus is always what? At the pole. And the directrix right here. So we can have all of those. Now, how can we have that? Well, I give you the equations. Here are the equations. So the ratio is the distance from the point to focus over distance from the point to directrix. So if this is our focus, right, and this is the directrix, so E is given by the distance from the focus to the directrix divided by that. So this divided by that. All right, and that's our E. So in the formula is EP, and P is actually the directrix. So if the directrix is vertical, then that means the conic is horizontal, right? And the equation of this is given by x equals to p. Now p could be positive or negative, right? Could be on this side or on that side. So it could be this way, or it could be what? It could be this way. And this is cosine in the formula. And if the conic is vertical, then the directrix is horizontal, so y equals to p is the directrix. Or it could be a negative p or positive p. So it could also be this way. And that's the directrix. Okay? So let's look at some examples. Here's one. So what kind of equation is that? Well, we're going to look at this, which is the general equation of a conic in polar with the sign, because this has sign. Now remember, in order to tell what this is, we have to make this 1 first. So this has to be 1. Then, so to make that 1, you divide everything by 3, right? So 6 over 3 is 2, 3 over 3 is 1, 2 over 3 is 2 over 3, and sine theta, right? So now what do we have? Well, E is 2 over 3, that's our E. So the ratio is 2 over 3. So that has to be, remember, if E is between 0 and 1, what do we have? We have an ellipse. So this is an ellipse. Now, if it's sine, remember, if it's sine, let me go back. So the directrix is y equals to p. So if it's sine is what? the conic with the focus at origin, directrix is horizontal. If it's sine, directrix is horizontal, right? So that means conic is vertical. So here, the E is 2 over 3, and EP is 2. So E times P equals to 2, but we know what E is 2 over 3P equals to 2. Equals to, what's 2 times 3 over 2 is 3, right? So P is positive, is 3, right? And Y equals to 3 is the directrix here, right? Y equals to 3 is the directrix, and the eccentricity is 2/3. All right, so the other two are similar. You have to make sure these are 1s. You divide so you get 1. But I'm going to show you in general what these look like when you graph them. Of course, we use computer to graph these things and work with them nowadays. So notice this is the cosine with the cosine. So this is horizontal and the directrix is vertical. I have here drawn both directrix, horizontal and vertical. So in case we change this, we have the directrix as well. So right now, this is an equation of an ellipse, right? And our E is 0.9. So if I change my E, first of all, I'm gonna go start from really close to 0. So we get a small, let me make this bigger. We can get something out of that. So we get, we get a really close, really small little ellipse, and then we make it a little bit bigger. So that's an ellipse, right? Now, if I go to 1, it turns into a parabola, and if it's greater than 1, it would be a hyperbola. See that? Now, P, of course, determines where the directrix is, and remember, we are talking about the vertical one, this one right here. So notice that if P is negative, directrix is to the left of the focus, which is pole, and if it's positive, directrix is on the other side. Okay? And this A and B are basically the way I graph this using polar, you see? That's using polar. As we turn around the circle, we graph this. This is when theta is that much, r is that much, and so forth. If you keep graphing it in polar, you graph this like this. So that's it. So that completes the one cycle of polar, and the rest of it just goes over this. It creates this shape in polar. All right, so that's it. That is the last thing I wanted to talk